Okay, so we have the law of reflection, and we want to use it as much as possible. It's so wonderfully easy and convenient. So maybe the first thought you have is let's just go crazy and let's go right to Funhouse mirrors or any mirror at all, and we'll figure out what's going on with these. And there are a couple of lessons that show up when you try to analyze a Funhouse mirror. So again, the hatch side means this is behind the mirror and this is the reflective side. So here's like a nice curvy mirror. And I've drawn one ray. So the one ray has the angle of incidence and the angle of reflection. You can see it there and there. So they're equal. There's normal coming normal to the surface. And I'll try to do this a second time and we'll see what happens. So why don't I put a ray come in here? Totally random. And what's normal to that? Well, normal looks like it's coming off here, and then angle of incidence equals angle of reflection. And what I can see is that I'm going to have these two things maybe a little bit too random because I didn't have a really nice result. If I extend these two rays, they're going to converge there. So clearly I get a Funhouse mirror that makes a really big image right here. So I'm not going to sketch it, but you could see they converge there. I could imagine an image there. What's the problem with that? Well, mathematically, the issue is that if I draw any two non-parallel lines, they're going to converge somewhere, right? Or if I trace them back, they'll make a virtual image on the other side of this. And if I draw a third ray, so maybe let's take a third ray about here. So what's normal to this? Normal to that looks about there-ish, comes off here. Ooh, this doesn't intersect with that at all. So it really takes a third ray to actually show whether or not any sort of mirror actually creates a coherent image. And in fact, one of the first lessons, or the first lesson, is that not everything that looks shiny creates what you would call a coherent image, where this thing, every single light ray that comes off of the object will converge or seem to converge in the case of a virtual image from a single point. So a coherent image would be something where every single light ray that I draw from the object actually goes through the same point or appears to have come through the same point. So this is not a coherent image, and in fact, not everything that's shiny will make one. And the other lesson that we have is in order to show that we have a coherent image, we'll need at least 3 rays to locate it. So 2 rays is kind of a brittle method because, again, any time I draw 2 non-parallel lines, they're going to intersect somewhere. So we're going to need at least 3 rays to locate an image. Okay, so fast forward a little bit, in the age of kind of modern manufacturing, we could talk about hyperbolic mirrors and lenses, and there's no reason why you can't make them. So sort of for historical accident and sort of because at least one of the equations is really easy in this case, we're going to talk about spherical mirrors. So we'll just take it for granted now and we'll go back and semi-prove it, at least kind of sketch out the proof, literally sketch out the proof, is that spherical mirrors do create coherent images. What is a spherical mirror? So imagine that I have a sphere, a mirrored sphere, a disco ball, if you will, but without plaquettes of mirror, like just really totally, completely shiny and smooth. And I just took the world's sharpest razor blade and I cut a piece off of it. So like slicing the end off of a loaf of bread. And I just took this hunk, kind of like the way that a contact lens fits over the eye, and sliced it off. And what I ended up with is something that looks like this. So it's a cap cut from a piece of a sphere. And, whatever, maybe looks a bit more like this. So cap of a sphere. So this size has nothing to do with the radius of the sphere itself. This size has to do with where we put the razor blade. So this thing has a center that would be where the center of the sphere is and a radius r away. So this is a sphere of radius r, and the size of the spherical lens in some sense has nothing to do with the radius r itself. So that's an independent thing. That's what's called the radius of curvature. It is not the size of the lens, which is a really common, annoying kind of red herring physics problem to distract or to throw at people. So we have two options. We could have a mirrored interior of our spherical shell, or we could have a mirrored exterior. So if you're looking at this thing and it basically looks like a bowl and the shiny part is the inside of the bowl, that's what's called a concave mirror. So concave, the mnemonic for it, or to help you remember, is that caves are damp. And you could imagine that if I use this, I could hold water on the mirror side. So a concave lens will hold water. Conversely, if we mirrored the outside of the disco ball in true disco ball fashion, this would be a convex lens. So if water rolls off the top of the mirrored side, that would be convex. So you have two options. These will be our spherical lenses, one of two possibilities. And it turns out that these things actually do create coherent images. Not everything that's mirrored does. And the kind of sketchy proof of that brings up another one of our geometric optics concepts, something that actually didn't exist for plane mirrors. And we'll define that first. So we'll call it an element. So an optical element could be a lens or it could be a mirror. So lenses will have foci too. Foci is Latin plural for focus, because I like being pretentious. So an element has a focus. So there are two ways of defining the light rays used to find a focus. One way is to say it's light from infinity. I mean, probably the moon is far enough, but light, actually 10 meters is usually more than far enough. So light coming from infinity has finished spreading out. So light from infinity, all of the rays will be parallel to each other, right? It's really far away. It can't spread out anymore. The other way of saying it is light parallel to the principal axis. And they're equivalent statements. I mean, in the age of lasers, I can make parallel light that's not at infinity. So either of these work. The important part is if this doesn't 100% click, which maybe it shouldn't because it's like half Latin and full jargon, we will draw this. So I've got some light coming in parallel to the principal axis or from infinity, and if it all goes through a single point, so that point is the focus. So let's draw it and see what happens. And yeah, lesson learned, no more purple chalk and no more red chalk, so we'll keep it to really bright colors. So here's a spherical lens. What type of lens is this? Yes, it's concave. So I've got a concave lens, and then I'll draw a principal axis that goes through the center of it. So there's my principal axis. So another way to understand what a principal axis is this is the center. So if you imagine the original disco ball from which this thing was cut, this would have been the center of the disco ball, and this is the little slice of bread that we took. Okay? So now what I'm going to do is start taking some rays and using the law of reflection. So first I'm going to have this ray coming in from infinity or parallel to the principal axis, and it's going to strike there. what a boring ray, right? So it is right along the normal. So the angle relative to the normal is 0, so it leaves the exact same way it came. So things start getting more interesting if we come in still parallel to the principal axis, but offset, maybe in this case above the principal axis. So, I kind of know what this thing will do, at least qualitatively. The normal looks something like that. We're going to get a better indicator of where it is, and it's going to come down, right? So, there's going to be some point at which these two things intersect. Now I know not to be tricked. I need more than two rays. So where is the normal? Well, if you think about a sphere and the geometry of a sphere, what the center does is the center tells you where the normal is. Right? So if I draw lines that come out of the center of a sphere and they hit the edge of this, those are my normals. So I'll take the center of this, which is 1 radius away. That's my normal. And now I can use theta I equals theta r. And I see that these things I'm going to cheat a little bit. Because, gotta forgive my really crappy drawing. Hey, look, that's more like where it should be. So theta I is theta r, comes out through there. We know not to be tricked by 2 rays. I'll give you a sneaky thing to do that doesn't help you. So now you're like, okay, I know I can't use 2 rays, I'll use a third one, but I know that this third one below the axis will come out, by symmetry through the same spot. That's not going to work. We need like a third fundamentally different ray. So maybe we'll bisect these and have this come in here. Okay, and I'll clean up my drawing a little bit. So from the center of the sphere out to here, so if I draw a straight line in between there and there, so that goes through there, and then I come out theta I is theta r, cleaning that up a little bit. So not a full proof, but kind of at least a sketch of a proof that all of these things are intersecting in the same spot. So at least qualitatively, you can see that as this thing comes closer and closer towards the principal axis, the angle is going to be shallower and shallower and shallower, and it's going to all be, approximately the same spot. So this is a focus. So a focus is defined to be if I have all these light rays coming in from infinity, they'll pass through the focus. So we teleported a little bit because we had a little bit of a battery malfunction. But we drew 3 lines, 3 rays, 3 fundamentally different rays, axis, far away, and middle. And they seemed to indicate that they were going to converge at some point that was closer than the radius of curvature. So in fact, you can prove that this point where all light rays that come in parallel to the principal axis, or quote-unquote from infinity, converge at is located actually just at r/2. So what we'll do with proofs in this class is we'll go over the proof when it's useful, like it teaches you something about how we reason in geometric optics. In this case, this one doesn't help too much, or it's kind of redundant. So just take it stated without proof that location of the focus is half the radius of curvature. And I'm going to put this in absolute value bars so we can generalize it to convex mirrors as well. Okay, so if this were a live class, what I would do is say, why don't you guys try to kind of repeat this hand-wavy argument not for concave mirrors, but for convex mirrors. So if you're kind of doing things honestly, what you can do is pause this and try it. And, okay, semi-hint there. I've got to redraw this. And what you'll get is probably correct rays. What won't make sense because we haven't really discussed why a focus is important is what we should say. Should we say the thing doesn't have a focus? Should we say it has a virtual focus? What's going on? So stop, draw some rays, figure out what's going on with 3 distinct rays for not a concave but a convex mirror. And here's the ray, and then we'll pick up in a second. So pause, unpaused. Okay, so here's the radius of curvature. And I'm going to use that to figure out where the normals are. So I got a light ray coming in along the principal axis, hits normal, comes back. I've got a light ray coming in like this. I'll use the radius of curvature to figure out where the normal is. And what the law of reflection says is I should come off like, yeah. And then I'll try a third one. So I come in like this. The radius of curvature tells me where my normal is. And then this angle is smaller than that one. So I get something that might look like this. And this doesn't look really that promising because I got a light ray leaving in this direction, I got a light ray leaving in this direction, and I got a light ray leaving in this direction. And these three are not going to converge, actually converge. But we have a way of thinking and talking about this when we talked a little bit about plane mirror images, is that it's not that they converge, it's that they appear to converge. And they appear to converge somewhere about here. And this is not a precise drawing, it's actually at r/2, just like a concave mirror. But they appear to converge on the far side of the mirror, the non-mirrored side of the mirror. So we're not going to say virtual focus. We're not going to, distinguish this in any way. We're just going to say this is where the focus is. So the focus for a convex mirror is going to be on the same side as the center, and it's going to have length. Don't believe that picture. Believe the proof. Still located here for convex as well. Okay, so concave, convex, if I have any sort of spherical mirror, this is true. What you guys got to remember is whether or not this is on the front side or the back side, and that'll dictate what the sign is. Okay, so who cares? So we didn't talk about why we would care about focus, and I'll put that here. And this is where we'll pick up with the next video, is that this could even be called like a theorem. It's so important. So I'll say optical element because it's true for lenses and for mirrors. So if an optical element has a focus, which is to say all light rays coming in parallel to the principal axis or from infinity converge at the same point, then it forms coherent images. So in this case, both of these have a focus, so both of them form coherent images. And again, this will be true for lenses too, lenses and mirrors. So that's fine. Our next question is, okay, where do they form them? And we'll have actually two answers for that. So we'll have a geometric answer, which are what are called ray diagrams. And we'll have an algebraic answer, which is the mirror equation. I love it when things have nice names. Astronomy's full of garbage names, like shooting star. It's not a shooting star. So we'll pick up with that in the next video. So both ray diagrams and mirror equations, so that's a little bit more lengthy one.